Hey everyone, Mr. Cummings here, and welcome to this video on the impulse momentum theorem. So in this video, we're going to be talking a lot about change in momentum. And so we know that momentum is an object's mass multiplied by its velocity. So if we have a change in momentum, we could have a change in the object's mass take place, or we could have a change in the object's velocity take place. And in this course, we're typically going to focus on problems where the object's mass is constant, but its velocity is changing due to some external force on the object or maybe a collision with another object. So remember that an object's velocity will change as a result of net force applied to the object over a duration of time. That's going to be important when we get into our derivation. So taking a look at the change in momentum equation, we know that the change in anything is just the final thing minus the initial thing. So change in momentum would just be final momentum minus initial momentum. We also know that momentum is mass multiplied by velocity. So if we want to expand this equation to have, instead of Pf and P initial, mass times final velocity multiplied by mass times initial velocity. So bringing that down, we see that we have a mass in both terms we can factor out. So what we really get here is that the change in momentum, providing the mass is constant, is going to be the mass of the object multiplied by the change in velocity of that object. And this is going to be one of the first equations that we start with when we derive our impulse momentum theorem. So to start deriving the impulse momentum theorem, we're going to use these equations at the top. And we're going to start with F equals ma. So this is just Newton's second law. And then we're going to plug in, for the acceleration term, we're going to plug in the identity for acceleration, which is acceleration is the change in velocity divided by the change in time. So what we get here is net force is equal to mass times change in velocity divided by change in time. So we're going to rewrite this. The force is the mass times the change in velocity over the change in time. And then we're going to use this other identity where we know that the change in momentum is equal to mass times change in velocity. So we're going to substitute this m times delta v term in our net force equation. We're going to say that the force is equal to the change in momentum of an object divided by the change in time. So now we're going to start with F equals change in momentum over change in time, or delta P over delta T. And we want to isolate delta P. So we want to move the time over to the force side. So we're going to multiply both sides of this equation by delta T. And that provides us with the impulse momentum theorem, which is that a force exerted on an object over duration time is going to change the momentum of that object, and we call that an impulse. So force multiplied by a change in time is an impulse, and the changed momentum of an object is also an impulse. So the impulse momentum theorem in its entirety is the impulse, denoted by the uppercase letter J, is equal to the change in momentum, delta P, which is equal to the average force exerted on an object times the time that force is exerted. So this describes the relationships between change in momentum, force, and time on objects during a collision. Something special to note here about this theorem is that each one of these terms, or the J term, impulse, delta P, and the force are all vector quantities. So the direction that we deal with for each of these quantities is significant, and we don't want to drop any negative signs or positive signs, and we want to be careful about that. So now we'll practice actually using this equation with a pretty straightforward problem. So we see we have a cart here that's traveling with an initial velocity of -3 meters per second towards some barrier, and then it's going to hit that barrier, bounce off, and it's going to be going to the right with a final velocity of 1.5 meters per second. So we know the impulse is going to be delta P, so we want to make a variable bank here of the information that we just collected from the picture and from the text in the word problem. So now we're going to get that impulse equals change in momentum, and we're going to expand that into the mass of the object multiplied by its final velocity minus the mass times the initial velocity. We'll plug in the numbers that we organized in our variable bank, and we want to make sure that we take care of our signs pretty deliberately. So we see that we're doing a minus mass times the initial velocity, but we have an initial velocity of -3. So we're going to cancel out those negative signs and make that a plus. So after adding these terms up and doing the arithmetic, we get that the impulse here is a positive 1.125 kilograms meters per second. And so we see that the object was moving negatively, so it had a negative initial momentum, and then the wall exerts a force on it, causing it to move right, so it has a positive final momentum. So we went from having a negative momentum to a positive momentum, so the impulse, or the change in momentum, should be in the positive direction, because that's the direction of our change. And now to continue this problem, we're going to take the information that we just solved for the impulse, or the change in momentum, and now we get some additional information. We know that the collision between the wall now takes 0.01 seconds to occur, so that gives us some time data. So we know we're going to use that other part of the equation. Impulse is the force multiplied by the change in time. So we'll go ahead and rearrange this equation for the average force by dividing both sides by delta t, and then we'll plug in our numbers here. So the change in momentum in the numerator is going to be the answer to our previous problem, so that 1.125 kilograms meters per second divided by this time of 0.01 seconds. So we get that the average force that the wall exerts on the car during this collision is 112.5 newtons. So now we're going to take a look at how could we do this exact same problem but analyze it experimentally. So we don't have any information given to us, we have to find it. So we're going to start by writing out the relevant equations here, and that will kind of give us a guide as to what we might need to measure and what equipment to use. And I also find it helpful to expand the delta P as mv final minus mv initial. And so there's two pretty reasonable ways to analyze the impulse experimentally of this situation. So the first one, if we were looking at the equation impulse is average force times the change in time, then we would just need to gather average force data and time data, or force data and time data together. So the way that we could do that is we would want the force that is exerted on the cart during the collision. So we could attach a force sensor either to the cart or to the wall at the point of collision, and we can allow the cart to run into that force sensor or to run the force sensor into the wall. And that will provide us, if we collect it using a computer, that will provide us with a graph of the force exerted on the force sensor over the duration of time. So we'll be able to use that force and time data to analyze the impulse on this cart experimentally. Now the other way we could conduct an experiment is to look at the change in momentum, or the impulse, as mass times final velocity minus mass times initial velocity. So looking at this equation, if we wanted to know these values, we need to know the mass of the object, so we could just use a simple electronic balance, and we could take the mass of the cart. And then we would need to know both the final velocity and the initial velocity of the cart. So we would want to measure or calculate the velocity at two different points. One way to do that would be to use a motion sensor. We could just put a motion sensor pointing towards the cart on the right-hand side of the cart, and then just measure the position as a function of time, and use graphical analysis to figure out what the initial and final velocity was. The other way to do this would be to just use a stopwatch and a meter stick. And ideally, when you're doing stopwatch and meter stick, it's helpful to use a slow motion camera to get really precise data there. But we could, assuming the cart is moving at a constant velocity, which we are, we could just take the distance and the time that the cart travels, and we could figure out what the velocity was entering the collision, and then what the velocity was after rebounding and traveling backwards. And so we see here, to analyze this experimentally, there's not really one official way to do it. In fact, a lot of experiments, there's multiple ways of doing it. You just want to make sure that we write out the equation and we're measuring the correct variables here. And that's going to be it on this video going over the impulse momentum theorem with some examples and some ideas of how to do it experimentally. Thanks for tuning in, and I'll see you next time.